Hello, this video is going to cover Chapter 6 for our introductory chemistry class. So our chapter is titled Chemical Composition, and this chapter is going to be all math. So I'm going to do pretty much one example problem per math type or per equation calculation for this chapter, and then we will do more during our Zoom time together. So we're starting with why do we care about chemical composition, kind of relating this to the real world. And the purpose behind this is we need to know numbers. So we don't just need to know that table salt is sodium and chloride. We need to know how much sodium is in something because it can affect our diet and our blood pressure. And we need to know how much iron is in a chunk of iron ore. The bottom example there is how much chlorine is in Freon. Freon's used in air conditioners or the air in your car, but the chlorine that's in it is bad for the environment. So all of these are examples of combining math with chemistry. Now, when you buy something, there's often three ways that it could be purchased. One is you're just buying the item, meaning if you buy one shirt, you're buying one shirt. But for things that are smaller or things that we buy in larger quantities, we don't normally buy them per item. We're buying them based off of how much they weigh. So if you go to the store and get a bag full of grapes, when you take it up to the register, they're not counting the grapes. So you're not getting charged 5 cents per grape. You're getting charged per pound. So the amount you're paying is based off of how much it weighs. Another way that we buy things is based off of a larger quantity. And a good example of this is eggs. We don't generally buy one egg at a time. We will buy a dozen eggs. And there's a lot of examples of this, and if you've worked in retail or have done, well, my job that comes to mind is I worked at a candy store for my high school and college jobs, and we would buy boxes of little cellophane bags that we would then put the candies we made in, and we bought those by the gross. A gross is 144. So there's all these numbers like that have set values. A dozen is 12, a gross is 144, and it's a way that we can count things that are generally sold or moved in larger quantities. Now, I talk about all this because atoms are really tiny. So we don't generally talk about just a couple atoms at a time. We need to be able to talk about a larger quantity. And so the number that we use for that is this guy right here, 6.022 times 10 to the 23rd. This is called a mole. So if we have 6.022 times 10 to the 23rd of anything, it's 1 mole. Now usually we're talking about atoms or molecules or ions, so we kind of generalize that and say particles, but we could have that many pencils and we would have a mole of pencils. Just like we could have 12 pencils and it would be 1 dozen pencils. So it's really just a way for us to have a group of items and give a name to that grouping. So this is also sometimes referred to as a chemist's dozen because it's the number that we use to count this. And there's a cute little mole there in their lab coat to remind us that October 23rd is National Mole Day because 10 to the 23rd, October 23rd, it's part of National Chemistry Week also, so something to keep an eye out for. So we're going to practice this. And at the top of the screen here, I have the start of our roadmap. And I'm going to make this bigger as we go through the chapter. But on the left over here, we have particles, which can be atoms, ions, or molecules. And on the right-hand side, we have moles. In the middle, we have the conversion factor. And notice that arrow goes both directions, so we can use this conversion factor to go in either direction. So our first question says, how many moles are in 5.6 times 10 to the 18th carbon atoms? So we are in atoms, and we want to convert it to moles. So we know that this is the right portion of our roadmap. It's also the only part we know right now, but we will add on to that. So we know our given. We know this is our given. We want to know how many moles. That's our find. And we know our conversion factor up there is the 6.022 times 10 to the 23rd. So I'm going to start with my given. 5.6 times 10 to the 18th carbon atoms. Now my conversion factor, 1 mole is equal to 6.022 times 10 to the 23rd particles. So instead of writing particles, I am going to write atoms and then mole on the top. Now the 1 goes with the mole. The 6.022 times 10 to the 23rd goes with the atoms. And then just like all of our other math we've talked about, we're going to cancel out our units. We're left with moles. We're going to put this into our calculator. And my calculator tells me 0.000009299. All right, a couple things. We want to check significant figures, but we also want to switch that over to scientific notation. It's not technically wrong the way that it's written, but it is difficult to read, and it is definitely easy to miss a zero. Your calculator might even have an option where it switches from standard to scientific notation for you. So when that answer is in your calculator, you might be able to just push that button. All right, so let's do our scientific notation first. There's my decimal place. I want my decimal place to end up right there. So we're going to do 1, 2, 3, 4, 5, 6. So I have 9.299 times 10 to the negative 6 because it was smaller than 1 to start with. We go back and look, and that number we were starting with has 2 significant figures. So I'm going to underline my 2 there. I look behind it. It definitely needs to round up. So what we end up with is 9.3 times 10 to the negative 6th moles. Now in the problem it does tell us that we had carbon atoms, but notice that didn't come into play. Just like if we had a dozen eggs or a dozen cats or a dozen cups, all of those would be 12. It doesn't matter what type of object it is we are counting. All right, we're going to go the other direction now. So this question says, how many gold atoms are in 8.83 times 10 to the negative 12th moles of gold? So this time, we are in moles, and we want to convert it over to atoms. So here's our given. I'm going to add moles here since it switched to the other line. And gold atoms is our find, and we know our conversion factor. It's up there at the top. So I'm going to start with my 8.83 times 10 to the negative 12th moles. The abbreviation for moles is just MOL. It's not a big change, but something I do want to point out because molecule, of course, starts with the same 3 letters as well. The abbreviation for a molecule is MOLEC. So something to keep in mind when you're reading the book, but also when you're making your own notes so that you don't go back and get confused by what you've written. And then I'm going to fill in my units again. I have moles on the bottom and atoms on the top. And there is 1 mole for every 6.022 times 10 to the 23rd atoms. And again, we put this in our calculators. So 8.83 times 10 to the negative 12th times 6.022 times 10 to the 23rd. And my calculator tells me, and it left it in scientific notation, which is helpful, 5.317426 times 10 to the 12th. Now, whether your calculator leaves it in scientific notation or switches it out really just depends on the brand. There are some settings where you can force it to stay in scientific notation the entire time. That's something I can definitely help you with, but also if you just, the make and model is at the top, so I'm using a TI-30XS calculator. If you look on YouTube for your calculator type, you can usually find a lot of information about it as well. All right, let's look at units. Moles cancel out, so we know we're left with atoms. Significant figures, we started with 3, so we're going to end with 3. So I'm going to underline that 1 right there. It's my third significant digit. I look behind it, and it needs to round up. So what we end up with is 5.32 times 10 to the 12th atoms. Okay, so we can convert from a quantity to a number of moles, or vice versa. Now, the number itself, 6.022 times 10 to the 23rd, is called Avogadro's number. That is Amadeo Avogadro over there. And where this number came from is that 1 mole of carbon-12 weighs exactly 12 grams. And remember, carbon-12, when it's written that way, that means that it has 12 subatomic particles. So for carbon, that means 6 protons and 6 neutrons. Now, 1 atom of carbon-12 weighs exactly 12 AMUs. And 1 mole of carbon-12 weighs exactly 12 grams. The number's the same, but that unit is very different. But because there's a connection between the mass and the mole, we can use this as our conversion factor. So that means that 1 mole of carbon weighs 12.01 grams and has 6.022 times 10 to the 23rd atoms. And so we can use that mass to convert between our moles and our grams. This number, too many clicks, there we go. This number is called the molar mass because it's literally the mass of a mole. So this number comes from our periodic table. Now, we've already used that mass on the periodic table. We called it the formula mass or the atomic mass, but that was when it was in AMUs. And so the number on our periodic table does have 2 values, which is a little confusing, but it is also really helpful because it means there's less information that you need to know. So when I look on my periodic table, it says that carbon weighs 12.011. That number, if we put the units as AMUs, is the mass of 1 atom. And that number, if we use grams, is the mass of 1 mole. Now we're going to use that as moles much more often because we don't talk about atoms individually very often. When we use it as a molar mass, the mass of a mole, the units are grams per mole. So that 12.011, I can write it as 12.011 grams per mole. And we are going to be using this as a conversion factor. So another way to write this out is 12.011 grams is equal to 1 mole. So here's a couple other examples going from hydrogen down to copper. So going from something that's very light to something that is much more heavy. And in that middle column, we're told this is how many pieces or particles are in 1 mole. Notice it's the same number all the way down that column because that's the definition of a mole. The last column is the weight of 1 mole. And this number is going to be different. So if we think about apples and grapes, How many apples are in a dozen? 12. How many grapes are in a dozen? 12. But how much does 1 dozen apples weigh? It's going to be 9 pounds around there, depending on the size of your apples. But what is the mass of 1 dozen grapes? That's going to be much smaller. That's probably not even going to be a pound. So this number here is just based off of counting, and this number is based off of size or mass. So we're going to use this as our conversion factor, and we've added on to our flow chart up here at the top. What we've added on is that we can convert from moles to grams, and our conversion factor is that molar mass. And so 1 mole is equal to some number of grams, which is called the molar mass, and this number is going to come from the periodic table. So we're going to do 2 problems here. We're going to go from grams to moles and moles to grams. And the question says, what is the mass in grams of 2.78 moles of sulfur? So I know I'm starting at moles and I want to end at grams. So 2.78 moles of sulfur. Now, in order to get my units to cancel out, I'm going to put moles of sulfur on the bottom and grams of sulfur on the top. Now, when we look at that conversion factor up there, 1 mole is equal to however many grams the periodic table tells us. So my periodic table says that 1 mole of sulfur is 32.065 grams. So we put that into our calculator. 2.78 times 32.065, and my calculator says 89.1407. So we do our regular checks. Units are canceling. I'm left with grams. I started with 3 significant digits. My 1 stays the same, so I end with 89.1 grams of sulfur. Okay. The second question says, how many moles are in 42.6 grams of copper? So we're going to go the opposite direction. We're going to start at grams and go back to moles. So 42.6 grams of copper. And my conversion factor, I'm going to put grams of copper on the bottom so that it will cancel out, and moles of copper on the top. So to fill in my units, I know that 1 mole is equal to some number of grams. I'm going to look at my periodic table down here. 63.546. Again, I'm putting that right into my calculator. My calculator says 0.67038. And I'm going to do my regular checks here. Grams are canceling out. I'm left with moles. I started with 3 significant figures. So there's my 3rd significant figure. Remember that leading 0 does not count. 0 is going to stay the same. So I end up with 0.670 moles of copper. Now, because that 0 at the very end is after our decimal place, it does count as a significant figure. All right, we're going to do a couple more in this category because we need to use the entire flow chart. Let's see. I'm going to move my little video over there. I think it's out of the way. So this says, what is the mass of 1.23 times 10 to the 24th helium atoms? So we're right here at atoms, and we want to know the mass. Now this is not a one-step problem. We have to go from atoms to moles and moles to grams. So we need to use that mole as our connector. So we're going to start with 1.23 times 10 to the 24th helium atoms. Now to go from atoms to moles, I know I'm going to use Avogadro's number. I'm going to put helium atoms on the bottom. I'm going to put moles of helium on the top. And then my second conversion factor, moles of helium on the bottom and grams of helium on the top. So I know all my units are going to cancel out properly. For Avogadro's number, I know that 1 mole is equal to 6.022 times 10 to the 23rd particles. In this case, atoms. And then for my molar mass, I know that 1 mole is equal to the number of grams on the periodic table. So for helium, that is 4.0026. So I'm going to put this in my calculator. Now, how you put this in your calculator can just depend on how comfortable you are with using scientific notation. One common way is to multiply across the top, write down your number, multiply across the bottom, write down the number, and then divide your two answers. You can put it in all at once, though, if that's something you feel comfortable with. All right, so my calculator tells me that the answer is 8.17535. So we need to do units, we need to do significant figures. Atoms cancel, moles cancel, we're left with grams. We started with 3 significant figures, so there's my third digit. I look behind it and it does need to round up, so I end up with 8.18 grams of helium. All right, last question on this slide says, how many atoms are in 48.9 grams of fluorine? So we're going to do the same steps, but in reverse. So 48.9 grams of fluorine. And I'm going to go from grams of fluorine into moles of fluorine. I need to use that mole as my in-between. We're going from grams to moles to atoms. And then my last conversion factor, I'm going to have moles of fluorine on the bottom and atoms of fluorine on the top. So I know all of my units will cancel. For that first conversion factor, I know that 1 mole is equal to the number of grams on my periodic table, 18.998. And in that second conversion factor, I know that 1 mole is equal to Avogadro's number, 6.022 times 10 to the 23rd. Okay, so I'm gonna put this in my calculator. Times 10 to the 23rd. And my calculator says 1.55003 times 10 to the 24th. All right, we're going to check units. We're going to check significant figures. Grams cancel, moles cancel. We're left with atoms. We started with 3 significant figures, so there's my last one. We check behind it. It will stay a 5. 1.55 times 10 to the 24th. Fluorine atoms. Okay, so there we go. We've done our 2-step problems converting from grams to atoms or atoms to grams. Now, we've done this with individual elements, but we can also do this with molecules. And the steps are not any different. The additional step that we would need to do is to calculate the molar mass of our molecule. Now, in our last chapter, we calculated formula mass. We took the number and the mass of each of the atoms and added them together to get a sum. So water, 1 molecule of water weighs 18.02 AMUs. If we have 1 mole of water molecules, it will weigh 18.02 grams. So notice that the numbers are the same, but this is the mass of one molecule, and this is the mass of 1 mole of molecules. So the numbers are the same. The size, though, the units are very different. So we're doing the same idea of a conversion factor here, but we're going to incorporate in the molecule side of it. Moles are in 1.18 grams of NO2. So we have grams, and we're being asked to solve for moles. So we're only going to need one conversion factor here. We need to figure out the molar mass of NO2. So our conversion factor, we're going to have grams of NO2 on the bottom and moles of NO2 on the top, and that's it. Now this does take a little bit extra time because we have to figure out the molar mass of NO2. So I'm going to put my math down here. I have 14.007 grams times 1 for the nitrogen, and 2 times the mass of oxygen, 15.999. So let me label these. This is my nitrogen, this is my oxygen. So I'm going to put this into my calculator. And we get 46.005 grams per mole. So now I can use that as my conversion factor. 1 mole weighs 46.005 grams. Now one thing I want to point out, you might have noticed this already, but with both these conversion factors, the 1 goes with the mole unit, and then the actual number goes with the other unit. Something to keep in mind because it can help you fill in those values a little bit easier. So now I'm going to do my math. 1.18 divided by that molar mass, 0.025649, and I'm checking my significant figures and my units. We know the grams are canceling. We're left with moles. We started with 3 significant figures, so those leading zeros do not count. 1, 2, there's my 3rd significant digit. It's going to stay a 6, so we end up with 0.0256 moles of NO2. All right, the question underneath it says, what is the mass in grams of 6.8 times 10 to the 12th NO2 molecules? So this time we're going to start over here in molecules. We want to end up in grams, so we need to go molecules to moles, moles to grams. So 6.8 times 10 to the 12th molecules of NO2. I know these units are long, but it is important to fill in your units so that you can see them canceling out. And then as we do move on to more complex math, it's going to be much more important to include those units. I say this because I felt like that just took up a lot of space. And then we're going to have molecules of NO2 on the bottom and mole of NO2 on top. And then last conversion factor, moles of NO2 on the bottom, grams of NO2 on the top. And then I can fill in my units. So to go from molecules to moles, I know I'm going to use Avogadro's number. 1 mole, 6.022 times 10 to the 23rd. And then I'm going to use my molar mass, 1 mole. And I've already calculated this molar mass in the previous question, 46.005 grams. All right, I'm going to put that one into my calculator. 6.8 times 10 to the power of 12 dividing it by Avogadro's number. and multiplying it by my molar mass. So I end up with 5.19485 times 10 to the negative 10th. So units and significant figures, molecules cancel, moles cancel, we're left with grams. We started with 2 significant figures, so that 1 is going to round up to a 2, 5.2 times 10 to the negative 10th grams of NO2. There we go. All right, the last side of this is using our chemical formula as a conversion factor itself. And we have a spider and a chair on here also. So a chair has 4 legs, which means if there's 4 chairs at your table, there's 16 chair legs. And we can do that in our head, but we can say if there's 4 chairs and one chair has 4 legs, then there's 16 legs at the table. We can do this with molecules as well, though. So this tells us that one water molecule has 2 hydrogens and 1 oxygen. So that means that if we had 4 molecules of water and we want to know how many hydrogens we have, well, one molecule has 2 atoms of hydrogen. So we would have 8 atoms of hydrogen if we had 4 molecules. So that chemical formula can be used as a conversion factor, as a ratio. So here's a couple more examples. If we have, but this is now switching it, instead of looking at it as molecules, because we know that's a very small value and we don't use it very often, instead we're switching it over to moles. So if we have 1 mole of sodium chloride, that means we have 1 mole of sodium and 1 mole of chlorine. If we have 2 moles of water, we have 4 moles of hydrogen and 2 moles of oxygen. 3 moles of calcium carbonate means we have 3 moles of calcium, 3 moles of carbon, and 9 moles of oxygen, because there's 3 oxygens for every 1 calcium carbonate. And then if we have 4 moles of C6H12O6, we're going to have 4 times as many of each of those. So 24 moles of carbon, 48 moles of hydrogen, 24 moles of oxygen. Our roadmap just got a lot bigger. It got twice as big. And the top half and the bottom half are identical. What's new is right here in the middle, we have that mole ratio. So if we want to convert from particles of one type to particles of another type, we're going to have to go all the way around this little ratio right here. Or if we want to go from grams to grams, we need to use that ratio. We can think of that mole ratio as the bridge between 2 different things. So for example, our question says, how many moles of oxygen are in 1.24 moles of Fe2CO3. So this is iron 3 carbonate. I am starting, let me switch colors. I'm starting right here. I have moles of iron 3 carbonate and I want to convert it into moles of oxygen. So I only need 1 conversion factor. I just need the ratio. And I know if I look at my formula right here, that carbonate is in parentheses with that 3. So if I multiply that through, I know that there's 9 oxygens in that formula. So I'm going to start with 1.24 moles of Fe2CO3. And this is going to have the same ratio on the bottom And on the top, we're just going to have our moles of oxygen, so that I know that in every one of those iron carbonates, there are 9 oxygens. Now, if I do the math here, my calculator tells me 11.16. So we're going to do our regular check. Moles of iron carbonate cancel. We're left with moles of oxygen. We started with 3 significant figures, so I need to do a little rounding. So I'm going to do that in the middle right here. So we're going to end up with 11.2 moles of oxygen. All right, we're going to do this one more time, but really in one of the more difficult ways. So how many grams of sodium, so I'm starting up here in grams of sodium, or that's where I want to end up, that's my find, are in 8.63 grams of sodium sulfate. So I need to convert from grams of sodium sulfate into moles of sodium sulfate using the molar mass, and then I'm going to convert from moles of sodium sulfate into moles of sodium using that mole ratio, and then from moles of sodium to grams of sodium using the molar mass of just the sodium by itself. 8.63 grams sodium sulfate. Touched in the wrong spot there. I'm going to fill in my units. We have grams of sodium sulfate on the bottom, moles of sodium sulfate on the top. So that's my first conversion factor. That's my molar mass. We have moles of sodium sulfate on the bottom and moles of sodium on the top. That's my second conversion factor. That's my mole ratio. And notice we're switching from one chemical to the other. In this case, we're switching from a molecule to an atom. Switching between 2 different things is, let me rephrase that. Anytime we want to switch between 2 different things, we have to use that mole ratio. And then my last conversion factor, moles of sodium on the bottom, grams of sodium on the top, and that will be my molar mass of sodium. So for that first conversion factor, we know that we're going to have 1 mole of sodium sulfate, and my molar mass, I already have it worked out for us. It is 142.04 grams. And for my ratio, I can look at my formula, and I know that in every one of those molecules, it contains 2 sodiums. So I'm just using my subscripts to figure that out. And then my last conversion factor, I can use my periodic table to say that 1 mole of sodium weighs 22.990 grams. All right, let's put this in the calculator. So 8.63 divided by 142.04 times 2 times 22.990, and my calculator says 2.79363. Let's check units and significant figures. Grams of sodium sulfate, moles of sodium sulfate, moles of sodium. We're left with grams of sodium. We started with 3 significant figures, so we're going to end with that. I'm going to underline my third digit, my 9, and it's going to stay a 9, so I end up with 2.79 grams of sodium. There we go. Now there is one more way to do this, and so the last problem we did was a mass to mass conversion, and there's one more way to do that mass to mass conversion, but it does require us to come up with an entirely new conversion factor, which really takes as much time as having all of our other conversion factors. So it's not really a time savings. I will show you how to use it on the next slide though, or in a couple slides. And this conversion factor is called a percent composition. And we have the equation down here in black. It says the mass percent of an element is equal to the mass of that element in the compound divided by the mass of the entire compound and then times 100. The red above it is just kind of a generic percentage equation. Percentage is always part over whole. If you want to know the percentage you got on a test, it's the part you got right divided by the whole thing. So let's put this into action. What is the mass percent of oxygen in magnesium nitrate? So that means that we're going to do the mass of oxygen in the compound. Now, to get the mass of the oxygen in the compound, I'm going to use the molar mass of oxygen and multiply it by how many there are. So in this equation, or this chemical formula, I know that there's 6 oxygens. So I'm going to take the molar mass of oxygen times 6 divided by the molar mass of that entire compound. So the top half of my fraction is going to look like this. The molar mass of oxygen, and I'm getting this from my periodic table, is 15.999 times 6. The molar mass of magnesium nitrate is 148.32. And then I'm going to multiply this all by 100 because we want it in percentage form, not decimal form. So 15.999 times 6, and I'll rewrite it one more time here. I get 95.994 divided by 148.23. And I get 64.76% oxygen. It's not really a sig fig thing for this one because we're just using periodic table masses. So leaving it at 2 decimal places is always a good measure for us. So what that number means is that when we have magnesium nitrate, whether we have 100 grams of it or just 1 gram of it, 64.76% of that mass is from the oxygen. And that means that the remaining 35-ish% is from the magnesium and the nitrogen. Now, I did say we could use that value as a conversion factor. Here's how. So our example is sodium chloride. Sodium, the mass percent of sodium in sodium chloride is 39%. So to turn this into a conversion factor, we kind of pretend that we have 100 grams of sodium chloride. So if we have 100 grams of sodium chloride, that means we will have 39 grams of sodium. And so we can use that as a conversion factor to convert from grams of sodium chloride to grams of sodium, or vice versa. So if you're given the mass percent, then we can use that as a very simple conversion factor. But if you're not given the mass percent, then going through our roadmap is really just as easy. How many grams of oxygen are in 44.8 grams of magnesium nitrate? So I have this mass percent. I'm going to go back up a couple slides. Oh, geez. Having troubles. There we go. 64.76. So I'm going to start with my given, my 44.8 grams of magnesium nitrate. And when I use that conversion factor, the way that my units are going to work is I'm going to have my grams of magnesium nitrate on the bottom and my grams of oxygen on the top. So for every 100 grams of magnesium nitrate, there are 64.76 grams. So I'm going to do my math. My calculator says 29.01255. Check my units. Grams of magnesium nitrates canceling out. We're left with grams of oxygen. We check our sig figs. We started with 3. So there's my third one. It's going to stay as 0. So 29.0 grams of oxygen. I like to cross through my zeros if I have a 0 and an O in the same answer, just to make it really clear. Not a necessity, just something I get in the habit of doing. So this is an alternative. The other way to do this would be to go from grams to moles to grams, like we did a few slides ago. But because we already had that percentage, it helped us out. In the last chapter, we talked about the difference between empirical formulas and molecular formulas. And the difference is that an empirical formula is the lowest ratio, and the molecular formula is how it actually exists. So notice these formulas here. They all have the same empirical formula, but their molecular formulas are different. And we have their molar masses here too. Notice that as we go down the line, they're each going up by 30. So there is a similarity between them. They're all multiples of 30. So the formula to go from there to there is times 3, times 4, times 5, times 6, and the masses would be 30 times 3, 30 times 4, and so on. So here's how we utilize this information. In a lab setting, if a new chemical is made, you can't always figure out its molecular formula, but you can figure out that overall ratio, the empirical formula. So then, with that information, you can do a little bit of math to figure out what the molecular equation would be. So here's our equation on the bottom. It says that if you take the molar mass of the molecular formula and divide it by the molar mass of the empirical formula, this is going to give you a factor to multiply your empirical formula by. It sounds a lot more complicated than it is. What is the molecular formula of a compound with a molar mass of 147 AMUs and an empirical formula of C3H2Cl? So this is our empirical formula, which means what we want to figure out, C3H2Cl, we're going to multiply this by some number so that we can get new subscripts. That's our goal. Now, to figure out what number we need to multiply that by, we need to find out how many times bigger the molecular formula is compared to this empirical formula. So I'm going to take the molar mass of the molecular formula divided by the molar mass of the empirical. Now we're given the molar mass of the molecular, 147. We're not given the molar mass of the empirical, but we can calculate it because we have our formula. So I'm going to do 3 times the molar mass of carbon plus 2 times the molar mass of hydrogen plus 1 times the molar mass of chlorine, and I get 73.5. So I do my math here, 147 divided by 73.5, and I get 1.999995, which is going to round to 2. This number that we're solving for, this n, this has to be a whole number. Now, if you get 1.99 or you get 2.001, those are close enough. You can round those. But if you get 1.5, 2.3, 3.7, those are not close enough. And that means that one of your masses is off. You put it in your calculator wrong. There's some type of error. All right, here's what we're going to do with that number 2. That tells us that our molecular formula is twice as big as our empirical. So I'm going to multiply those subscripts so I get C6H4Cl2. And that is my molecular formula. All right, this is our last slide. Thanks for sticking in there. I know there's a lot of math in this chapter, but we will do a lot of practice in Zoom.